Molweni, Sawabona, hello, and thank you to the organizers for this opportunity to talk to you about radio astronomy. I thought I'd start with a quick advert for our symposium on all-inclusive AGN, which will be taking place as part of the IAU General Assembly being held in Cape Town next year. And this will be showcasing all of the latest results in AGN research, including multi-wavelength studies, multi-messenger studies, and also incorporating the latest results in terms of simulations in addition to observations. And just to properly introduce myself, my name is Sarah White. I'm a postdoctoral fellow funded by the South African Radio Astronomy Observatory and affiliated with Rhodes University. And today I'll be talking to you about the brightest and faintest sources in the radio sky. And my research focuses on active galactic nuclei. So what are those exactly? Well, we're thinking about the types of galaxies where there is gas or material falling onto the supermassive black hole at the center. And typically this forms an accretion disk, this whirlpool of gas surrounding the supermassive black hole. And then beyond that, we have something that we refer to as the dusty torus. And then if you imagine at much larger radii, that's where we have the stars that belong to the host galaxy for this AGN. And in about 10% of cases, we have the production of these radio jets, which brings us on to, well, why do we care about studying active galactic nuclei? Well, ultimately, we want to understand how do galaxies grow and evolve over cosmic time. And for this, we need to understand how does that supermassive black hole influence its surroundings. And we know there's a huge amount of literature that shows there's a co-evolution between that supermassive black hole and the host galaxy. So the black hole grows through black hole accretion, and the galaxy grows through star formation. And for the radio loud sources, which is the tip of the iceberg, just 10% of the AGN population, these are obviously much brighter in the radio, and so much better studied than their radio quiet counterparts. And from existing work, we know that those radio jets can impact on their surroundings. They can either trigger a molecular gas cloud to collapse and form stars, or it could completely disperse that gas. So we're already quite familiar with the amount of kinetic feedback we get from AGN. But just to keep in mind that in both cases, the radio loud and the radio quiet AGN, we have the presence of this accretion disk, which produces a huge amount of emission over a wide wavelength range, including a large amount of thermal energy. And to remember that if we have gas that is too warm in the host galaxy, it will no longer have the conditions required to collapse and form stars. So that's why we really do need to consider the entire population in order to better understand how galaxies evolve. Of course, this subset of the population is much harder to study because they typically belong below the radio flux density threshold of most radio telescopes. So to start with, we have, with the radio loud sources, we have a sample known as the GLEAM Jansky sample. So this is a selection of nearly 2,000 of the brightest radio galaxies across the southern sky, selected thanks to the GLEAM survey, which is at low radio frequencies and conducted using the Murchison Wide Field Array in Western Australia. And with this sample, we have something that is 10 times larger than the 3CR sample of the Northern Hemisphere. And why is that important for our work? Well, we want to understand how do the properties of radio galaxies evolve, not just as a function of redshift, but also as a function of environment, because the amount of gas that's available in these systems is important for both fueling the AGN and also fueling the star formation in that host galaxy. Now, whilst GLEAM provides us excellent constraints at the low frequency end, we also have follow-up data that extends our radio spectra up to 5, 9, and 20 gigahertz, thanks to the Australia Telescope Compact Array. And we find that for our subset of 200 sources, out of the full sample of 2,000, 76% of them follow the usual power law description. So this is what we tend to use to describe the synchrotron radiation from these objects. And you can see that if you actually put together these broadband radio spectra, there's much greater variety in spectral curvature than you may expect. For about 16% of cases, we have these convex or peak spectrum sources. So the idea here is that maybe we have a young radio galaxy that's present. Those radio jets haven't been able to burst free of the cocoon of gas surrounding the supermassive black hole. Or maybe this turnover is just due to there being absorption of the low-frequency photons by ionized gas. And then in about 8% of this subset, we note from checks against the literature that these these U-shaped spectra tend to be coincident with blazars. So that's where we're looking down one of the radio jets of the radio-loud galaxy. And in a few cases, we have these particularly unusual radio spectra. So that's where there's a kink in the radio spectrum, which we wouldn't have been able to pick up if it wasn't for the contiguous frequency coverage provided by the MWA. So originally we thought, well, maybe this is just because the MWA beam is very large, and so it's blending two unrelated radio sources together that gives rise to this superimposed, this total radio spectrum. But we followed them up already with MeerKAT, and they remain unresolved. So it may be that we need to go to higher resolution still to resolve this object into two components, or we could genuinely be observing a single AGN, but witnessing different epochs of activity, with one epoch of AGN activity giving rise to this kind of more curved structure here, and another past epoch of activity giving rise to this part of the spectrum, and that those two are then combined to form this total radio spectrum. So this is one area of that needs to be worked on further in order to understand the black hole accretion histories of these sources in the same way that we are interested in the star formation histories of the host galaxies. And for 140 of the GLEAM-4-Jansky sources, we followed them up with MeerKAT, which even with just 5 minutes on this amazing radio telescope, we get exquisite images, and this is one of my favorites. We have this, in the low resolution, we would refer to this as a Z-shaped radio galaxy, but thanks to the excellent sensitivity and resolution of MeerKAT, we can pick out this beautiful helical corkscrew-like structure. And one explanation for this is that we have the supermassive black hole having its radio jet axis becoming perturbed for some reason, and that causes the jet axis to then precess in kind of a spinning top-like motion. And the image I show in the bottom right here is a radio image of an X-ray binary, S433. I've put them side by side just to show that we seem to have the same phenomena happening on just very different scales. So on the left, this is the origin being a supermassive black hole, and on the right, the origin being a stellar mass black hole. And despite these being the brightest radio sources across the southern sky, we still don't actually know that much about them because there just isn't enough spectroscopic information available in the literature. And so that's why we have this ongoing multi-semester campaign on the Southern African Large Telescope, which is allowing us to go over 4 orders of magnitude deeper than the current spectroscopic survey called the 6-degree field galaxy survey. And that is giving us crucial redshift information so we can actually calculate the intrinsic properties of these sources, such as their radioluminosity and also their angular size. So how many of this complete sample of radio galaxies are actually giant radio galaxies. So any subset of the GLEAM-4-Jansky sample will inherit the completeness of the parent sample.
Now, we are at 9 minutes.
Great, perfect, thanks. So I've been focusing on the radio loud part of the AGN population, but there's also a lot of work still to be done, of course, for the radio quiet AGN. They're more difficult to detect. And crucially, the trickiest part is how much of the radio emission is due to star-forming regions in the host galaxy, and how much of that faint radio emission is actually connected to AGN activity. And this is an area of active debate in the community. And one of the methods that we can apply to do this, to disentangle those contributions, is to make use of the far infrared to radio correlation. So this is observed for For star-forming galaxies, of course, where you have stars forming, a lot of dust is produced, it absorbs energy and re-radiates in the far infrared, giving us this x-axis measurement. And where you have stars forming, you also have stars dying. And it's the supernova remnants and those shock fronts that are left behind that accelerate electrons and produce the radio emission, giving us our y-axis measurement here. So we see a very tight correlation for a wide variety of star-forming galaxies, including our nearest neighbor, the Andromeda galaxy. So where does our sample of radio-quiet AGN lie with respect to that far-infrared radio correlation? So that's indicated by this one-to-one relation shown here. And so any sources where the radio emission can be explained by star formation, we'd expect them to lie along this line. But the fact that we get a slight majority of the sources lying beneath this line suggests that actually there's another process taking place, another process that's contributing to the total radio emission. And so we have evidence that actually the AGN is significant in these sources. I note that this is all new work combining deep data from MeerKAT and new spectroscopic redshifts from SALT. And with the deeper radio flux density that MeerKAT enables, we're actually finding that we're picking a larger fraction of the star formation that's present in the host galaxy. So that's why these results, so it will be published hopefully in the next couple of months, are less pronounced than previous work. So to summarize, it's crucial that we have this low radio frequency information if we want to better understand the life cycle of radio galaxies and all the different processes that can be revealed by having broadband radio spectra. For about 200 sources, we have follow-up up to 20 gigahertz, thanks to the Australia Telescope Compact Array. We have beautiful images thanks to MeerKAT from 140 sources. We'd like to look into how prevalent is precession across the whole sample. And of course, those spectroscopic redshifts are crucial for doing some really basic science. It's vital that we get good spectroscopic completeness across the whole sample. And then with MeerKAT and in preparation for SK-MID, by going to the lower radio flux densities, we can start to better understand that 90% of the AGN population, which are termed radio quiet. And previous work showed that the black hole was dominating the radio emission, so this was actually very controversial at the time. This was my thesis work, PhD thesis, and around then, everyone just assumed all of the radio emission must be star formation. There aren't any powerful radio jets present, so it's all star formation. So this was actually kind of a game changer in the community, and it's thanks to MeerKAT that we can actually go to much lower radio flux densities and pick up at more of the star formation in the host. Nkosi, and I'm now happy to take questions.
Thank you.